So after learning about static electricity, we are now going to learn about electric current. First, what is electric current? Electric current is the flow of charges. And what are these charges? These charges can either be the positive charges and negative charges. However, from what we have learned already, between positive and negative charges, which charges actually flow or transfer from one object to the other? It is the negative charges. However, when we discuss this, we will also use positive charges to make conventions, or meaning to make our model easier to understand. Now, there are two conditions that should be met in order for electric current to flow. Okay, wait. When will electric current flow? There are two conditions that we need to meet or should be met in order for electric current to flow. Number one, there should be a complete closed loop in the circuit. Okay, a complete closed loop from the positive terminal of the circuit or the power source, such as the battery, to the negative terminal. Again, complete closed loop from the positive terminal to the negative terminal. And the second condition is there should be a push. There should be something that will push the charges to flow along the circuit. Okay, and this push will give energy to the charges so that they can flow. Okay, what do we mean by the closed loop? For example, we have a circuit like this, and this is our battery. This is the positive terminal and the negative terminal of the battery. And this is the lamp. These are the wires. And this is the switch. How can we consider this as a closed loop? This will be a closed loop if we close the switch. So this time we have a closed circuit. And this closed circuit should close a loop from the positive terminal of the battery, connecting it to the negative terminal of a battery. Okay, what is it that we don't consider as a closed loop? So, which is not considered as a closed loop from the positive terminal to the negative terminal of a battery? For example, we have this battery here and we connect a wire to it. If we connect the wire this way, is this a closed loop, complete circuit from positive to negative? No, it's not. Maybe it's a closed loop, but it's not a complete circuit from the positive to the negative terminal. Later on, we will find out why we need this closed loop from positive to negative terminal. So, in order to better understand the push, which is the second condition in order for electric current to flow, we will make an analogy first. Okay, but we are going to talk about energy, specifically potential energy. Okay, so for example, this is the ground, and let's make a stair, and we have a ball. Wait, I'll assign this as position A, and I'll assign this area as position B. For example, we have a ball. We have a ball here. At what position is the GPE, or gravitational potential energy of the ball, greater? Position A or position B? Okay, so due to its location from the ground, the ball will have a greater potential energy at position B because of its height. And it will have a lower potential energy or gravitational potential energy at position A because it is closer to the ground. Now, we know that gravitational force I'll just assign this as gravity. Gravitational force is directed downwards. Now, if we have the ball here, and we want the ball to change position from position B to position A, will it move naturally from B to A? Yes, it will move naturally because of gravitational force. Remember, gravitational force is directed downwards. So when it moves from position B to position A, this is its natural movement. Okay, it will move naturally downwards. So when it moves from B to A, what happens to its potential? Its potential energy is lost. Okay, so loses potential energy. Now, what if we move the ball from position A to position B? Will the ball naturally move from position A to position B? No, it will not. What should we do in order for the ball to move from position A to position B? Okay, we need to do work on the ball. Remember, work is the transfer of energy from one object to the other. So, if we apply work to the ball from position A to position B, did the ball gain or lose potential energy? It gains potential energy. Why? Because we did work on the ball, meaning we transferred the energy from us to the ball. Okay, so from this discussion, we can say that this area B here is the area of high potential. And area B is the area of low potential. Okay, now why are we discussing this? Because we are using this as an analogy so that we can better understand the push that is needed to move the charges around a circuit or to make an electric current. Okay, let us now apply the previous analogy to electric charges. For example, we have a positive charge here. We know that this positive charge exerts electric force, and we can assign the convention as the direction of that convention is out of the positive charge. Now, let's have a positive test charge. What is a positive test charge? This positive test charge is just a convention because we're trying to make a model in order to understand how electric charges behave, or we're making this model to understand how the macro or the bigger picture of things happen. Okay, so for example, this positive test charge is being affected by the electric field from this positive charge. Now, if we have this next to this, how do you think they will behave with each other? Will they attract or will they repel? Since they are like charges, they will repel each other. So, what's the natural thing for this positive charge to do, or what's the natural movement for this positive charge? Will it move towards this charge or away from this charge? It will naturally move away from this charge. Okay, it will naturally, this is its natural movement, move away from this specific charge. Okay, for example, let's assign positions again. Position A, position B. If we are going to change the position of these positive charges from A to B, will this positive charge gain potential or lose potential? It will gain potential. Why will it gain potential? Because in order for this positive charge to move from position A to position B, we need to do work on it. And when we do work on it, we are transferring the energy to this positive test charge. However, if we want to move this positive charge from point B to point A, do we need to do work on it? No, we don't need to do work on it. Why? Because again, this is the natural movement of this positive charge when it is affected by this positive charge. Okay, so when it moves from B to A, will it gain or lose potential? It will lose potential. Okay, so we say that this area B is an area of high potential and this area A is an area of low potential. Okay, so let's have a different situation. Let us now have a different situation, but we still have a positive test charge. What if we have a negative charge here? Okay, so this positive test charge will be affected by this charge such that they will be attracted to each other. So the natural way for this positive charge to move is this way. It's its natural way. Oops, sorry. How do I do this? Okay. This is the natural way of the movement of this positive test charge. So let's assign again. Area A, area B. If this positive charge moves from A to B, will we do work on it or no work is needed to move it from A to B? Okay, since it's a natural movement, no work is needed to move the positive charge from A to B. So if it's no work, will it lose or gain potential? It will lose potential. But in order to move this positive charge from B to A, since this is not the natural movement for this positive charge when it's affected by this negative charge, we need to do work on the positive charge so that it can move from B to A. So if we do work on the charge, what will happen to its potential? Will it lose or gain potential? It will gain potential. So in this situation, we can say that this A is an area where there is high potential and B is an area where there is low potential. Okay, so let us now apply what we have just learned about high potential and low potential area in terms of electric charges here in an electric current. So here, this symbol, this diagram, is not the circuit symbol for a battery or a cell. The circuit symbol for a cell is this one. This is the positive and then this is the negative terminal. I just did it this way so that we can better visualize what happens. And this one is the circuit symbol for a lamp. Okay, so if this is our battery, we know that this end is the positive terminal and this end is the negative terminal of the battery. And if we are going to draw electric field lines, we know that electric field lines go out of positive and into negative. Okay, so I'll erase that line first. Okay, what if we have a positive test charge here? This positive test charge will be affected by the electric field produced when this positive terminal is facing this negative terminal. How will this behave? This will be repelled by the positive terminal, and this will be attracted to the negative terminal. So its natural movement is towards the negative. Natural. Okay, so if this is the natural way for the positive test charge, we know that if it moves from this position to the negative terminal, it will lose potential. Okay, however, we do not want the low potential. I'll discuss that later, sorry. Okay, now in order for this positive test charge to gain potential, we need to do work on it. Okay, we are going to do work on it so that it will move towards the positive terminal. Do work. Now inside a battery, there are chemical processes that happen such that they will push the positive test charge towards the positive terminal. So that's what a battery is doing. Okay, inside chemical processes. Why do we want to push this positive test charge towards a positive charge? So that it will gain potential. Okay, so if it moves towards a positive terminal, it will gain potential in this area. Okay, so gain potential. Okay. And then, once this charge goes out here, by the way, this is what we call, inside the battery is what we call as the internal circuit. Outside the battery is what we call as external circuit. Now, when this charge has already moved out of the battery, it is now part of the external circuit. What's the natural way for this positive test charge to move? Its natural way of movement is to move away, because it will be repelled by the positive terminal. To move away from the positive terminal and be attracted towards the negative terminal. So, what do you think happens along the process? Since this is the natural way for the positive test charge to move in the external circuit, will it gain potential or lose potential? Okay, during this process, it will lose potential, such that when it goes back to this negative terminal, it has lost most of the energy that it originally carries. Okay, so we say that this negative terminal is an area of low potential, and this positive terminal is an area of high potential. If there's low and there's high, we say that there is potential difference. Okay? Always remember, this electric current will only flow if there's potential difference. That is the differences in the potential between the positive terminal and negative terminal of a battery. If we have, for example, both low at the same amount, we won't be able to push the charges around. Okay? Okay, so now that we have understood what the potential difference is, sorry for the spelling, how do we now define potential difference? Potential difference is the amount of energy that a single charge carries. So remember this one. So for example, this battery has 1.5 voltage. So the battery is doing work on the positive charge in moving it from negative terminal to positive terminal, such that when it reaches this part, the charge has already gained 1.5 volts. Okay, that means this single charge has already gained 1.5 joules. So that's what we mean by potential difference. Amount of energy that a single charge carries, or 1.5 volts is the same as 1.5 joules per coulomb. Okay, so sorry, the SI unit, remember, for energy is joules, represented by capital J. The SI unit for charge is capital C, or coulomb. And the SI unit for potential difference is volts. Or potential difference is also known as voltage.